Okay, so let's start. This time we have proper long chalk, not like always. So okay, so so last time we discussed the different formulations of this string sigma model, right? In particular, we proved the equivalence of the Nambu-Goto action and Polyakov action. And we discussed that in either of these formulations there is reparametrization invariance. So to the or diffeomorphism invariance, which is a gauge symmetry in this model. So you can make arbitrary parameterizations of your coordinates, or coordinates were tau and sigma, that we called sigma 0, sigma 1, right? And so you can reparameterize sigma alpha, is sigma alpha of some new set of coordinates, alpha equals 0 and 1, and well, with the condition that the Jacobian is positive, so sigma 0, sigma 1. Well, even classically, to have having this kind of reparameterization invariance is not that good for the visual theory of differential equations, because it means that there is some functional arbitrariness in your solution. So to have a uniqueness of solution and so on, one should fix a gauge prior to solving the equation, or even prior to formulating the Cauchy problem. We're mostly interested in the Cauchy problem, right? Like we have some curve that's evolving in time, right? It's sweeping the minimal surface or extremal surface and so on. So I would like to fix the gauge for this invariance. Fix the gauge, and this can be done, of course, in an infinitely number of ways, but some ways are better than others, and in practice only certain gauge choices are used. So the gauge choices that we will study and that are usually studied are the following. So the two main gauge choices. So one is called conformal gauge. So this is some kind of analog of the gauge where we set E of tau equals a constant for the particle case. Well, the kind of drawback of this gauge is that the constraints will still remain. So the constraints have to be imposed on top of your equations of motion. So the constraints become constraints on initial data for the equations of motion. So some constraints remain. So same like we had the constraint that p squared plus m squared equals 0, again for the particle case. So in this gauge E of tau equals constant, we had additionally this constraint. But the nice thing about this gauge is that the Lorentz symmetry is not broken. So or in general, Poincare invariance remains. So Poincare invariance is explicit. So right, in principle, when we fix a gauge, in principle, we could accidentally kind of break some of the symmetries that we have. Of course, in a good situation, that doesn't mean that these symmetries are gone, but rather that they're hidden somehow. In a bad situation, it might mean that symmetries are also gone, but we'll discuss it later. Kind of at face value, we just expect that if we had a symmetry and we fix a gauge in a bad way, so that we break the symmetries, then they are hidden somehow, because the theory should be gauge invariant after all. So this is Poincare symmetry, is just the global symmetry of our theory, of our two-dimensional theory, right? Same kind of logic applies to other target spaces. For example, if we don't have flat space, but we have some space with isometries, then conformal gauge will preserve those isometries in general. So these are the isometries of the Poincare group, is the group of isometries of the flat metric, right? So the other gauge that we will consider is the so-called light cone gauge. And actually, we will be talking about it today, most of the time. Light cone gauge. So here, the upside of this approach is that we can solve the constraints explicitly. So constraints can be solved explicitly. So in the case of a particle, you can also have a light cone gauge in the case of a particle, but it's somewhat less illuminating there. Why it's useful? Because, well, particle is kind of simple case anyway. We can solve in any gauge, right? We know they just have straight lines, and that's it. But in case of a particle, we had the static gauge, remember, where kind of compare the static gauge, which was x0 equals tau, right? And then we solved p0 as a square root of p squared plus m squared. So you see in static gauge, we also solved the constraint explicitly. So kind of the same kind of logic. We want to solve the constraint explicitly. But the drawback is again that, well, here it's that SO1, so the Lorentz symmetry and also Poincare symmetry broken explicitly. Again, this is the same like in static gauge, where we choose one preferred coordinate, so it kind of formally, I mean, naively breaks Lorentz invariance just to rotation invariance, right? Then Lorentz invariance is preserved, but we have to somehow prove it. So these are the two types of gauges that are usually considered. Yeah, and today we'll focus on this light cone gauge. And next time we will study conformal gauge. Well, the upshot is that they will give the same results, because the theory is supposed to be gauge invariant. But the way these results come up is quite different in the two cases. Okay, so to introduce light cone gauge, first we rewrite the metric in light cone coordinates. So we have the target space metric, and d minus 1. So we pick out, we choose one coordinate here, x1. x1. And then we have and this we will call dx plus dx minus, where x plus minus is by definition 1 over square root of 2 x0 plus minus x1. So these are the light cone called light cone coordinates. And everywhere below this capital Latin index will run from 2 to d minus 1. So these are all coordinates except these light cone coordinates. These are, we will call them transverse coordinates. Okay, so the Minkowski metric in these coordinates has the form that, as you see from there, just 0, minus 1, minus 1, 0, 0, 0, 0. So just like that. And the scalar product of two vectors, VW is minus V plus W minus v minus W plus sum over V A from 2 to d minus 1. Well, the slight complication that one has in light cone gauge is that you have to be careful in raising and lowering the indices, right? So, for example, V plus is minus V minus, and V minus is minus V plus. So we will use both upper and lower indices, but so you have to. There is a difference whether you have indices upstairs or downstairs, so there are some minus signs, so kind of one has to take care of that.
Sorry, can you explain what the eta is?
Eta is just the metric tensor of this metric, yes, so this is it's a more or less standard notation for Minkowski metric, so eta mu just this. Okay, so we already recalled the kind of static gauge for the particle. So this was the static gauge for the particle. So let's a little bit let's derive the Hamiltonian. So this is the Hamiltonian, right, in the static gauge. So let's derive it once again in a slightly different way. Let's first consider the particle. Particle. Let's get back to the particle. So this is one-dimensional case. As we so first of all, in the case of the particle, P0, the momentum, which was dl over dx0 dot, is minus m x0 dot over square root of minus x dot squared. So maybe I'll say first we start with static gauge. Yeah, static gauge. This is for the particle. So the static gauge is x0 equals tau. So in this gauge, the momentum is minus m over square root of minus x dot squared. So in particular, this is negative. So we have the constraint that p squared plus m squared equals 0. So we can solve this as p0. So p0 is negative, so p0 is minus square root of p squared plus m squared. So, or easier to use p with upper, 0 is square root of p squared plus m squared. And the Lagrangian, so the Lagrangian we had here was, if you remember, this is just p mu x mu dot. And now we just substitute in here our gauge constraint, so x0 equals tau. So what we get is sum over pi xi dot I from 1 to d minus 1 plus p0, right? Maybe I'll write a capital P just to be sure. Plus p0. So this is, you see from this we read off that this is minus the Hamiltonian. So the Hamiltonian is precisely p0, which is square root of p squared plus m squared above. So that's another way of deriving the Hamiltonian. Basically, first you write the Lagrangian in first order form, and then you substitute the gauge condition directly in this expression. Yeah, so we substitute. And this is quite a convenient procedure in the general case, so you can do this kind of thing in the general situation. So first we'll study the light cone gauge for the particle. So this was static gauge, but light cone gauge is technically similar. So light cone gauge says that x plus equals tau. Okay, instead of x0 equals tau, we said x plus, where x plus was that light-like coordinate, x0 plus x1, right? And so the meaning of this is the following. So we have our light cone. This is x0 versus x1. We have the light cone. And then we have our time-like curve. And so in the case of in the static gauge, basically what we were doing, we were projecting a given point on the time axis, right? We were parameterizing the curve by the time axis, and this time we will project onto the light cone. So yeah, and we should also kind of, so this is a 90-degree angle, and then we have here L. Here we have L prime. So this line here, and this is x0 plus x1 equals L prime. right? So it's a curve with a kind of 45-degree angle, and when x1 is 0, then x0 is L prime, right? So the intercept is kind of L prime, and so there's an equilateral triangle. So L prime is square root of 2L. So L is 1 over square root of 2 L prime, so x0 plus x1. So this is x plus. Right, so we're parameterizing our curve by this coordinate on the light cone. We're projecting all points here and like that, instead of projecting it here in the static gauge. Clearly, it's a one-to-one map also because the curve is time-like. So x dot squared. So this is a time-like curve. Which means that x dot squared is negative along this curve. Maybe draw it more. So that's why we can choose this gauge. Yeah, we just project on a different axis, kind of. But at this point, it might seem like it's just a more complicated way of parameterizing the curve. However, the profit is in some technical simplification of the Hamiltonian. And let's see how it happens. So the point is that the constraint, we still have the same constraint. P squared plus m squared. So this is minus 2 p plus p minus plus m squared equals 0. And so we want to solve it for the variable conjugate to the coordinate variable that we've eliminated by the choice of gauge. So we eliminate all canonical variables in pairs, right? We set, for example, x plus equals to tau, and we have to eliminate p plus from the constraint. Same like in static gauge, we set x0 to tau, and we eliminated p0. So so p plus is minus. So p plus is the conjugate variable, that's minus p minus. And so we solve for p minus here. So p minus is 1 over 2p plus times sum of pa squared plus m squared. Okay. I mean, when I say conjugate variable, so all like, momenta and coordinates are paired in the usual way, right? So if we write the Lagrangian, this is p mu x mu dot. So this is representation variant. I mean, this. I mean, you can has the same formula in any set of coordinates, right? So, for example, this is p plus x plus dot plus p minus x minus dot plus pa x a dot. Yeah, so that's where we read off which variables are conjugate to which, yes? So p's and x's have indices in opposite places, right? So, I mean, it's easy to get confused at this point, I mean, with all these pluses and minuses. So p's have indices downstairs and x's have indices upstairs, and they're conjugate in exactly that way. There's no metric involved here, okay? This is just a canonical one form. I mean, the pullback of the canonical one form, yes? But we raise indices or lower indices with a metric. after that. So we define p's with upper indices as contractions of p's with lower indices with a metric. Same for x's. And that's just done for some convenience that in some formulas, to get rid of the, say, minus signs, we pack the minus signs in the definition of our variables. So, that's how it works. Okay, and so now by the same logic as we did before, this thing is 1 now. All right. So so we get this p minus x minus dot plus that, and this becomes minus the Hamiltonian, right? So by this logic, this becomes minus the Hamiltonian in light cone gauge. So the light cone Hamiltonian for the particle is minus p plus. So this is p minus, and we substituted from here. So this is 1 over 2p plus. Maybe I'll write minus 2 p minus times okay. So this is minus the Hamiltonian. So minus the Hamiltonian. So Hamiltonian is minus p plus lower plus, which is p minus, and p minus is this. And then I re-express this p plus as minus p minus. Why I do that? Because p minus is one of my remaining variables. Okay, I want to go back to the canonical variables. So this is the light cone Hamiltonian in the case of the particle. And of course, like I said, in the case of the particle, this is it's just a matter of taste, what you want to use, which gauge you want to use, because they're all equally simple, kind of. But morally, the logic is that now the Hamiltonian is quadratic in almost all variables, right? The Hamiltonian is now quadratic in p's, as opposed to the static gauge Hamiltonian, right, which we which we just wrote out just before, which was square root of p squared plus m squared. So we had this square root here. Again, in this case, it's doesn't matter. It doesn't matter that much, but in the two-dimensional case, it will matter whether we have a square root or not.
So can you repeat again why this is minus HLC while the first term is minus?
That's just by definition that Lagrangian is px dot minus the Hamiltonian. So whatever we have here should be identified with minus the Hamiltonian. So we discussed that in the case of we said first that the Hamiltonian is kind of 0 here, right? We discussed it in previous lectures, but then we had the constraint on top of that, right? P squared plus m squared, which we imposed by Lagrange multiplier. So that's another way of dealing with it, is to solve explicitly the constraint, to fix a gauge and solve explicitly the constraint. In that case, we don't have the constraint anymore, but we should plug in here the solution of the gauge condition and the constraint, which is what we're doing here. So and same thing applied in the static gauge case, where we read off the Hamiltonian in this way. This was p0 square root of p squared plus m squared. So
can you explain this again, that in Lagrangian we assume that h to be 0, Hamiltonian, but here we have some Hamiltonian.
yes, because we've reduced also the number of variables, right? So we've reduced by one set of canonical variables. So we solved the constraint explicitly, and we fixed the gauge. And that's kind of a different system now, with a dimension 1 less, and a Hamiltonian, which is derived in this procedure. But this is equivalent to dealing with a system in dimension 1 higher and imposing constraints.
So here we are working in dimension lower.
Yes. I mean, that's the point of fixing a gauge, right? You effectively reduce the dimension of your system. Yeah, one coordinate is removed by the gauge constraint and one by solving the constraint equation. But these formalisms are equivalent somehow, even if it's not that obvious. But I mean, somehow by construction they have to be equivalent. So yeah. So working in the full theory and imposing constraints is what we will do in conformal gauge. So this was like having the gauge E equals a constant, right? Where we had equations of motion for more variables, but the initial data were subjected to the constraint, which is p squared plus m squared equals 0. Here we have unconstrained system, so there's no constraint on initial data. But to go back to the full system, one has to substitute the additional variables are solved in terms of the like physical variables or whatever, the independent variables. So yeah, so this is the Hamiltonian in light-cone gauge, and it might not be obvious in this case, but I mean, the simplicity might not be obvious in this case, but the kind of the key idea is that here we have a quadratic expression in the p's as opposed to square root of the p's. So it's kind of reminiscent of a free system. Although one still has some small nonlinearity here, but that will not matter so much as we will see. Okay, so this is the light-cone gauge for the particle. Now we'll do the light-cone gauge for the string. By basically repeating this procedure to some extent. So light-cone gauge in 2D case. So of course, this is where you will see the difference between static gauge and light-cone gauge. Okay, so one option for strings would be to choose some analog of static gauge, which would be so one option is to choose x0 equals tau, and say why not choose x1 equals a sigma, where a is a constant. So this is one option. Sometimes it's called Monge gauge. So here we have arbitrariness worth of kind of two functions, right? We can reparameterize two functions. There we had only time variable. Here we have time and sigma variable that we can reparameterize. So we can expect that we can fix two gauge constraints, right? We can fix two functions to given values, kind of. So one option would be this one. So basically, we just measure time along target space time, and we measure sigma along the projection on in a space-like direction in target space. Yeah. So the string is in target space. Let's imagine that its configuration is such that it's projected one-to-one onto some axis. So there are, of course, various problems with this gauge. So, for example, it might curve, and the projection might not be one-to-one, for example, right? Then we have to project on another axis, and so on. But this is in general typical of gauges. So gauges can miss some configurations, so they might not work kind of globally for all. Yes, but still, okay. Let's say in a sufficiently large amount of configurations, it's fine. We can project on some axis, right? But so first of all, the problem with this is that this does not respect the closed condition for the string. So it does not apply to closed strings, right? Because x1 is not periodic. But technically more essential drawback is that the Hamiltonian will be highly nonlinear. So Walsh Hamiltonian highly nonlinear. So this is kind of homework to derive it. So in the same way like we just did for the case of the particle, you can derive the worldsheet Hamiltonian and find that it's some terrible square root that you would not want to deal with. So that's why we don't want to use this Monge gauge. Although it might be useful for some particular applications and so on, for open strings stretched between two planes or something like that. So sometimes in some limits maybe it's useful, but that's not what's useful for quantization of the string later on. So we will not universally use it. So the better choice is the light cone gauge. So again, we have a larger freedom than in the particle case, so we can fix two functions. And just like before, we will set x plus equals tau. So one can argue that this can be done because we assume that tau is such a coordinate that dx over d tau is always a time-like vector. So basically, for a fixed sigma, x of tau is a kind of particle trajectory. So you can always project by the same logic as on the picture before. You can project it to the light cone. And the second gauge choice will be that p plus, which is minus p minus, and this will be some f of tau. So when I say f of tau, I mean that this is independent of sigma. Okay, so we can fix p plus to be independent of sigma, and its dependence on tau, we cannot really fix it by gauge choice. We will see that it's a kind of gauge invariant thing. So this will remain an independent variable in our theory. But we can eliminate the dependence on sigma. That's the point. We will see why it works. But this is the so there are two gauge conditions, and these are the gauge conditions. So the point of this gauge is that the constraints can be solved explicitly. So let's recall the constraints. So we had constraint C1. So which was p mu x mu prime. So this is p plus prime plus p minus prime plus pa xa prime equals 0. Okay, let's write first the second constraint. So constraint C2 was p squared plus squared prime squared, which is minus 2p plus p minus plus pa plus t squared times minus 2 x plus prime x minus prime plus some xa prime xa prime, and that's also 0. So what are the simplifications that occur here? Well, first of all, x plus is tau, so x plus prime is 0, right? Exactly, this is 0, but same thing here. So this is 0. Then p minus, we fixed p minus. So more exactly, we haven't completely fixed it, but it doesn't depend on sigma anymore. So the idea is that we solve these equations for x minus prime and p plus, respectively. Right? So this is solve for x minus prime. So x minus prime is 1 over p plus sum over pa xa prime t minus 1. And so the second constraint we solve for p plus. So more exactly, p, yes, so p minus 1 over 2 p plus sum over, this is pa squared plus t squared all the various minus signs are again absorbed into these plus minus variables. Well, p plus, p capital plus is independent of sigma, but it might be dependent on tau. This is basically the same variable that we had in the particle case. So in the particle light cone gauge case, there was this p plus in the denominator as well. And so here it doesn't depend on sigma as opposed to all the other variables, right? So this is kind of a particle-like component remaining, which is in principle dynamic component. So this way we've solved the constraints explicitly. So the idea is that we can completely eliminate the x plus minus p plus minus variables. The set, so x plus is tau, x minus is solved from here as an integral. Then p plus is some function of tau, and p minus is solved in this way. So we impose two gauge conditions and we solve two constraints. This way we get rid of 4 variables, right? 2 sets of canonical variables. X plus p plus, x minus p minus. And all the variables that remain are these transverse variables, which are pa and xa. And one small thing remaining here, which is the fact that p plus is p plus of tau.
I think we need to find the commutation relation. So we will write down now the Lagrangian, just like we did before, plug in those conditions, right? And the first part of the kinetic part of the Lagrangian, which is like px dot par, that gives the Poisson brackets, right? So far we don't have commutation relations because this is classical theory. But yes, we have Poisson brackets. Yes, and by the way, so what remains is, so far, I mean, to be completely clear, so what remains is this p minus of tau, right? So there's p minus of tau. And accordingly, there is still a x minus, kind of x minus of tau, small x minus of tau, which is the only piece of tau that cannot be solved from this constraint, right? So x minus of tau is say 1 over something like 1 over pi times the integral of x minus of tau x minus of tau sigma d sigma. So there's still one mechanical mode remaining of x minus. So this guy, which doesn't depend on sigma, it cannot be found from the constraint because the constraint has only a derivative of x minus prime. So you can shift x minus by something independent of sigma, right? So I'm saying that what the sets of variables that remain are PA of tau sigma, XA of tau sigma, and these two small guys that don't depend on sigma. Okay? This is like the average of x minus over sigma, okay, to be clear. More exactly, maybe I'll write, so there is a small difference in open and closed case, because remember, sigma goes from 0 to pi or 0 to 2 pi. So x minus of tau is 1 over pi, x minus of tau sigma d sigma from 0 to pi. This is an open case, and 1 over 2 pi, integral from 0 to 2 pi. Closed case, okay? It's just some notational thing. Anyway, the point is that there is some small mode remaining here. And we will write out the Lagrangian in a few moments. One thing that we've achieved is that we've explicitly solved the constraints by eliminating two sets of variables. Okay. Second thing is that the Hamiltonian, the worldsheet Hamiltonian that we will get is quadratic, will be quadratic in the p and x variables, and therefore the theory is linear in this gauge. That's another thing. But it was also linear in the case of the particle, but there it was not so. It was not as useful as it is in the two-dimensional case. But first, before we write out the Hamiltonian and the Lagrangian, let's explain why this gauge choice is possible. So the point, well, x plus equals tau, like I said, it works the same way as in the case of the particle. So we assume that there is at each point there is a dx over d tau squared is time-like, so you can project on the light cone. But then, to justify the second gauge choice, we have to actually write out the expression for p plus. P minus is p minus is dl over dx minus dot. And this looks explicitly as follows. So this minus t x dot times x prime, x minus prime, minus x prime squared times x minus dot over the square root. And now let's see how it simplifies once we pick the first part of the gauge. So x plus is tau. This x minus, this x minus. So x minus is minus x plus, right? So this is minus 1, and this is 0, right? So that's once we pick the first part of the gauge choice. So minus t x prime squared over the square root Okay, so once we've fixed x plus, we still have functional freedom in our reparameterizations, which is to choose, so tau is tau tilde, and sigma is sigma of sigma tilde tau tilde. Right, so we don't want to change tau anymore because x plus is equal to tau. But we can reparameterize sigma in an arbitrary way. And again, we assume that d sigma over d sigma tilde is positive. This is the Jacobian of this change of variables. Of course, so the derivative, so you see what stands here is the derivative of x. So under these reparameterizations, this expression will change, right? And using precisely this, we want to say that we can fix p minus to what we want. So of course, so dx mu over d sigma. So this is x mu prime. This is dx mu over sigma of sigma tilde. So this is over d sigma tilde times d sigma tilde over d sigma. And as a result, so if you see there is a second power of x prime in the numerator and effectively the first power in the denominator because you're taking a square root. Each of these guys transforms by square of d sigma tilde over d sigma. The square root will transform as the first power. So the point is that p minus tilde is p minus times d sigma over d sigma tilde. So p minus is multiplied by the Jacobian. And the Jacobian is kind of an arbitrary function. So one might think that you can basically set p minus to an arbitrary, say, constant, right? So p minus was some function, but we multiply it by another arbitrary function. But that's almost true. So that's almost true, except that there's still one gauge invariant object, which is the integral of p minus, right? So this kind of means that p minus is kind of a one form, right? So we will call p small minus. So p small minus is the integral of d sigma of p minus, and this is the same as the integral over d sigma tilde p minus tilde. Of course, we assume that our reparameterizations respect boundary conditions. So 0 goes to 0, pi goes to pi, or whatever. Or if it's closed string, then this is a periodic function and so on. Yeah. So this guy is independent of reparameterization. So this is p minus of tau. So this is gauge invariant. So there is one function of time that we cannot fully fix, which is why we can set p minus to some function of tau, right? So I mean, this guy is then just minus say pi times f of tau, right? So that's the same function that. So this is open and well. I mean, closed is minus 2 pi times f of tau. Closed. So anyway, what I want to say is that by doing this kind of reparameterization, the integral of this guy remains invariant. So you cannot change it. But the rest you can change. So the integral is the so-called zero mode. So something that doesn't depend on sigma. Right? The average over sigma. And that's like I say, that's perfectly consistent with what we're doing, because the constraint also doesn't allow us to express the zero mode of x minus, right? Because that's the derivative. So the overall shift cannot be determined from here, the overall constant in sigma. So this guy, I mean. So the point is that this x minus is conjugate to this p minus, and they still remain in the theory. Okay, now let's write out the Lagrangian. So we've solved the constraints.
I'm sorry, I don't really understand. If small p minus is sigma independent, why would it follow that capital P minus is sigma independent? Or do we say that because of the Jacobian being like another function we compare?
Yeah. So we do a reparameterization to make P minus sigma invariant.
Oh, we can say that the Jacobian takes care of this.
Yes. Yes. I'm saying that at face value, you just have some function and you multiply by another arbitrary function. So in principle, you think that maybe we can set it to a constant, just like we did for square root of x dot squared. Remember, for the particle? There is a gauge where square root of x dot squared is a constant, right? Or e is a constant. Right, we multiply. Our logic was that we have some function of time, we multiply it by another arbitrary function of time, so we can set it to a constant if it's not zero, let's say, right? So here I'm saying there's a small caveat in that argument, because the integral of this thing is gauge invariant, so you cannot, and a priori it's a function of time. So that's an obstacle to setting p minus to a constant, but you can set it to a constant in sigma, right? So just time dependent, not sigma dependent, okay? I mean, the obstruction is in this integral being the gauge invariant. But like I say, it has to be the case, because also x minus, the integral of x minus over sigma cannot be determined from the constraints. So it's a remaining, there's one x minus remaining and one p minus remaining. Okay, so now let's write out the Lagrangian. And well, we'll write out the Lagrangian, but our goal is also to determine the Hamiltonian that will follow. So first, well, recall that the action is the integral over d tau of the Lagrangian. So by Lagrangian, we mean the full Lagrangian, not the Lagrangian density. So the integrated Lagrangian, okay? So it's the integral over d sigma of p plus x plus dot plus p minus x minus dot plus pa x a dot. So sum over from 2 to d minus 1. This is the Lagrangian. And now, well, x plus dot is 1, right? And p minus is independent of sigma, as we saw this, independent of sigma. So now we want to simplify this expression using that, and we're integrating over sigma, right? So what we have here is d sigma pa xa dot. That's just how it was before. Plus p minus times the integral over d sigma of x minus dot. Or let's write this as d over d tau of integral of x minus
d sigma, right? And then we have minus integral of p plus over d sigma. So this will be the Hamiltonian, light cone Hamiltonian of the string. So what happened here is that we just took p minus out of the integral, outside of the integral, because it's sigma independent. And we just changed the order of integration and differentiation. Now we will use our notation. So the notation for these averaged quantities will be that, well, like I told you before, so x small minus is like 1 over pi integral x minus d sigma, or 1 over 2 pi. So this is from 0 to pi, or 1 over 2 pi. I'll write it again. X minus d sigma from 0 to pi to 2 pi. So this is open and closed. And p minus is always the integral d sigma of p minus. So this is pi times p minus in the open case, and 2 pi in the closed case. So this just, I'm just saying that there is some factors of 2 in closed versus open case. So for example, this guy is p minus x minus dot in both cases, right? So the light cone Hamiltonian, so you should use p plus from this formula here. Okay, so let's put an arrow here. So p plus is expressed from the constraint. P plus, lower plus is minus p minus. So one finds that the light cone Hamiltonian is the integral of p minus d sigma. And this is minus 1 over 2 p minus integral over the sigma pa squared plus t squared xa prime squared. This was the upshot of this calculation. So remember, in the case of the particle, we had a similar expression, but we had no integral over sigma, and we had p squared plus m squared. Here, there is this integral and this kind of term. So the nice thing about this is that now the Hamiltonian is basically quadratic in the variables. You see? In the PA and XA variables. The only nonlinearity sits in this P minus, right? But one easily sees that the equation of motion for P minus, so P minus dot is minus dH dx minus, but it doesn't depend on x minus, so this is 0. So P minus is just a constant. And the equation for the conjugate variable x minus, so x minus dot, is p minus over p plus. So that x minus is p minus over p plus times tau. Well, I omit the x0 is 0. Let's assume x0 is 0. So this I just derived from the Hamiltonian, right? So, or from the Lagrangian, if you wish. I just vary with respect to x minus this gives p minus dot, and there's no dependence on x minus anywhere else. Right? The idea is that you should think about this as kind of infinite dimensional mechanics, yes? So in particular, p minus and x minus, they're just a usual pair of canonical variables. Let's just vary with respect to x minus. You get minus p minus dot, and there's no x minus anywhere else. When you vary with respect to p plus, you get x minus dot, and then there is p minus here in the denominator. So you get 1 over p minus squared, right?
I'm sorry, I have a question. We get that p minus, small p minus is constant, which means that capital P minus is constant from this formula.
That's right.
But we've said that the integral over the sigma of p minus is, we can't choose p minus to be constant.
We can't choose it by choice of gauge. I mean, it still remains as a dynamical variable that we have to write equations of motion for. But ultimately, it becomes a constant on the equations of motion.
Okay.
So that thing about p minus not being a constant, I mean, that's just, strictly speaking, needed for the theory, but ultimately, it is a constant, I mean, for all practical applications, let's say. Yes, so everywhere else, p minus will be a constant because it's a constant on the equations of motion. Okay, but it's not because of choice of gauge, it's because of equations of motion. Yes. So, and then, I mean, I hope you understand this formula, right? This is just, I differentiate the Lagrangian Hamiltonian with respect to p minus. I get minus 1 over p minus squared. And what was here was p plus, p lower plus or p upper minus. So, I mean, you get this ratio. Is it clear where this ratio comes from? I mean, what stands here is p minus, right? This is p small minus. So now I differentiate with respect to p lower minus. I get the same thing divided by p minus, which is what I've written here. No, these are small variables. Yes. I mean, I differentiate this guy with respect to, well, here I differentiate with respect to p small minus, but p small minus and p capital minus, they are differ by a factor of pi or 2 pi. Just the reason why I keep p capital minus here is because I want this to be a universal formula for open and closed case. Otherwise, you get a factor of 2 somewhere. So anyway, that's not really that important. I mean, these are just some technical complications. The important thing is that we solve the equations of motion. They say that p minus is a constant, and basically all the rest, if p minus is a constant, that all the remaining equations are just linear equations for pa and xa, right? Because this is now genuinely quadratic. This guy is a constant now. So that's the okay.
Can I ask another question?
Yeah.
Yeah. Is p plus then also a constant? Because when we differentiate with respect, integrate with respect to tau, we assume it's a constant, but I don't see why.
P plus, which p plus? P small plus?
Like x dot minus equals p minus divided by p plus, and then we integrate with respect to tau, and then we assume like the lower p plus is a constant.
Yes, p minus is also a constant because this is the Hamiltonian in a time-independent system, right?
Okay.
I mean, just think about it again as mechanics. This is the Hamiltonian. There's no explicit time dependence, right? So yeah, So this guy is a constant because of this, and this guy is a constant because it's a Hamiltonian, and it's that's good. Yes. So okay. So now we will do some manipulation with this Hamiltonian. So we will diagonalize this Hamiltonian now. Like I say, it's the equations will be linear equations, but still they need to be solved in some explicit way, right? So maybe I'll just write it here. So x plus is tau, and p plus minus p minus is f of tau. This was our gauge.
So this we've solved a little bit, part of the equations. So let's diagonalize the Hamiltonian. So first we'll do that for the case of closed strings. So now we'll have to make some assumption which theory we're dealing with. So closed strings, and that means that we impose periodic boundary conditions. So A of sigma plus 2 pi and PA So that means that we can expand in Fourier series, right? Let's expand in Fourier series. So XA is going to be XA of tau plus sum over n not equal to 0, A and A of tau over square root of 2 pi. And accordingly, PA will be PA of tau over 2 pi plus so this is just Fourier series. And you see precisely XA is the small XA is the average of capital XA, and PA is the integral of PA, capital PA. So then there are some reality conditions. So reality conditions X and P are real. So that means that A minus NA is A and A star, and B minus NA B and A star. And let us now substitute this into the Lagrangian that we had before and get rid of the sigma integral, right? Now we can do the sigma integral because we've expanded everything in explicit Fourier harmonics. So our Lagrangian will have the following form. So it's PA XA dot. Well, I mean, I hope it's clear what the sums are. So then you get B and A minus NA dot plus 1 over 2 P minus minus 1 over 2 pi PA squared plus have this formula. And so you see the sums from here, the sum is just over A. Here is both over N and A. And likewise there, right? So this is A, and N not equal to 0. And here is A, and again N not equal to 0. So what remains from the two-dimensional setup is the fact that we're summing over n's. We have an infinite number of modes of Fourier harmonics.
Otherwise, it becomes pretty much a just mechanical system with infinitely many variables, right? And now we'll diagonalize the Hamiltonian. I mean, it's almost diagonal, but still there's something we can improve on, because so far the equations of motion tell you that kind of A dot is proportional to B and B dot is proportional to A. So we want to like fully diagonalize it. So the good coordinates are alpha and A is 1 over square root of t to t, B and A plus IT and A and A, alpha tilde So here again, n not equal to 0, otherwise n arbitrary integer number. So the claim is that once we do these linear combinations of B's and A's, the Lagrangian will take an even nicer form. And you just substitute it in the Lagrangian. And you get, and this is PA XA dot, as before, plus sum 1 over IN plus 1 over 2 p small minus sum PA squared plus sum 4 pi t sum of alpha and A. Okay. Okay, so that's the expression. So it's kind of homework, derive this expression. I mean, do the algebra, plug in these expressions, and I mean the expressions. Express B and A in terms of alpha and alpha tilde, plug into that Lagrangian, check that everything works this way. And this is a manifestly diagonal. So this is now the kinetic piece, right? And this is minus the Hamiltonian. So this is the Hamiltonian in the px alpha alpha tilde variables, right? And this alpha and alpha tilde are called oscillators. So oscillators, because the Hamiltonian is literally the Hamiltonian of harmonic oscillator, right? So I hope you know that the Hamiltonian of harmonic oscillator can be written as, I mean, even the Lagrangian. So the Lagrangian can be written as A I A bar A dot minus omega A bar A. Yeah, you're familiar with this? I mean, A is some x plus IP or whatever, P plus IX. So omega is the frequency of the oscillator. That's one way of writing the Lagrangian and Hamiltonian of. So this is the Hamiltonian of harmonic oscillator. So now if you look at this Lagrangian, you see it's an infinite sum of such oscillators. Right? You have, so alpha minus n is alpha n bar. So you see alpha minus n is, so it follows that alpha minus a star. I mean, bar is star, okay? So, I mean, if you're star. So what stands here is alpha n star, alpha n dot, and then there is a according piece in the Hamiltonian, which is alpha n star, alpha n, right? The only small difference is that here there is a factor of n here in the kinetic term. Of course, it can be attributed to a normalization of these oscillators, right? You could rescale them, but usually people don't rescale them, but they actually, somehow it's a convention, they keep this non-trivial Poisson bracket. So again, it's like kind of homework to derive the Poisson brackets. So the Poisson brackets are alpha Ka, alpha Nb is K delta AB, delta K plus N. Same thing with alpha tilde Ka, alpha tilde Nb is K delta AB, delta K plus N. And then the mixed bracket is 0. So alpha and alpha tilde is 0. So the present, so you can derive those Poisson brackets by looking at this kinetic term here. Yes. So secretly, what stands here is the symplectic structure, or which is what is the same as the Poisson structure, Poisson bracket. So the presence of the factor of k, you should not forget it here, right? There is a factor of k. This is because you're dividing by k here. Okay. And maybe the final thing that we will discuss today is that there's still one constraint remaining, although we have almost solved all constraints. But from this thing here, we see that there's still one constraint remaining, namely if we integrate this thing over sigma, there's still some constraint appearing. So let's integrate it over sigma. So this, so integrate over sigma. And you get that integral of x minus prime d sigma from 0 to 2 pi. And all variables are assumed periodic, including x minus. So this is 0, so this has to be 0. On the other hand, this is minus 1 over p minus integral over d sigma of pa xa prime from 0 to 2 pi. And once you substitute the expression in terms of the a's and b's, this is I n a n a b minus n a. And now you substitute the expression for a's and b's in terms of the alpha and alpha tilde, and you get that this is minus 1 over 2 p minus sum over alpha n
alpha minus n a minus alpha tilde n a alpha tilde minus n a. And so this is 0. Okay. So this is this guy standing here, these two sums, they're called levels. So levels, for a reason that will be clear later when we quantize this thing. So n is by definition sum over alpha na alpha minus na, and n tilde is by definition sum of alpha tilde na alpha tilde minus na. So this constraint says that n is equal to n tilde. So this is called a level matching constraint. So we kind of almost fully solved the system, right? We've written the Lagrangian and the Hamiltonian in an explicitly quadratic form with these oscillators. In principle, one can solve these oscillators satisfy oscillator equations, so we can solve them. But there is a condition on initial data, which is that n should be equal to n tilde. So it's easy to see that n and n tilde are conserved quantities, because the oscillators, this one's multiplied by the exponent, this one's multiplied by the inverse exponent. They cancel, so these are conserved. So this is some constraint on initial data, which comes from this original constraints that we had from the start. So that's the classical theory of closed string in light cone gauge. So let me recap that. Light cone gauge is convenient because you can explicitly solve these things in this way that I've mentioned. Like homework for you to compare that's not the case in a generic gauge, like say this Monge gauge. You can write out the Hamiltonian. It will be some ugly square root and unclear what to do with it. This is kind of usually thought of as a physical gauge, meaning that all the remaining degrees of freedom are physical, so not subject to almost any other constraints. As opposed to conformal gauge, where we will have some unphysical degrees of freedom, the ones that have to be then constrained by the constraints. Okay, so and then we'll do next time we'll continue we'll do the same thing for open strings, and then we'll pass to conformal gauge and study conformal gauge, and then we'll do quantization in both light cone gauge and conformal gauge. That's the plan for the nearest couple of lectures. And next time there will be no lecture, so the next lecture is in 2 weeks from now. Okay, thank you. Goodbye. See you soon.